Hi, this is Pratima back with you again. Let's start the module 3 of your waves and optics. Hope you have followed all the concepts of module 1 and module 2, and even we have solved the numericals also. If you want to go back and look into the module 1 and 2, you can look into the description box where you can find out the links. So now what does this module 3 consist of? This comprises of two parts. One is the lasers and the another one is the fiber optics. So let's start with lasers now. In this video lecture, I'll just give you the history of laser. How many years are we ahead of now? Is there any speciality in the year now, which is 2020? And what are the characteristics and the basic concepts of lasers so that you can understand the beauty of laser in it, which can lead to number of applications which are around you and which are about to come in the near future ahead. So starting with the history of laser. In 1951, C.H. Townes, he gave the idea of maser. So he just wrote it on a paper with his student and sitting on a bench on a beautiful evening, and that was the beginning of the maser, which is microwave amplification by stimulated emission of radiation. In my coming slides, you will know what is stimulated emission of radiation more. And I do remember that you all have learned all these things in your plus 2, but if you can recall all of them and apply more so that you can go ahead a bit of the advanced studies of the construction of the laser, it will be more good for you. So moving ahead with this idea, they were able to demonstrate this first maser using ammonia. And this was the first device based on Einstein's predictions, which obtained the first amplification and generation of the electromagnetic waves, which are light, by stimulating it. So how do we stimulate light and all we'll see in the coming lectures. Moving ahead, they were able to, 1 year ahead of it, they were able to design and build oscillators in order to amplify and raise the intensity of the produced stimulated emission of radiation. So they named it and they were able to understand it as something which is an antonym of absorption, and hence they named it as a negative absorption. And they also named the mechanism of building up this intensity or the amplification of the intensity as pumping method. This was done by Basso and Prokhorov in their labs. And 1 year ahead of it, they were able to develop the microwave solid state maser in Harvard University. That was done by Bloembergen. So 1 year ahead of it, even they were able to advance this technique from the microwave wavelengths to optical lengths. So they were able to sketch or plan for the early optical maser. Again, this was done by Townes. So he could enhance his knowledge or apply his knowledge of microwave onto the visible range. So 1 year ahead of it, they were able to publish, Townes along with his student Shallow, they were able to publish this operation of lasers in both optical and infrared regions, so that, and they were able to even propose how well it can be accomplished. So it didn't start here, but it was able to move ahead, that in 1960 they were able to prove it so much that Townes and Shallow were given a patent in 1960 for the laser, which was then called as an optical maser. Okay, so microwave amplification of stimulated emission of radiation in the optical region, which is the emission of light, they called it as, which is being stimulated and radiated out. So they were granted a US patent with this number, and hence 1960 is considered as an invention of laser, though much research have been started 6 years before of this. So from 1960, in the year 1960, this is a very special year where they could even construct different types of lasers from different media. In like 2 months ahead, 2 months ahead, they were able to construct the first laser in a solid state medium by using a ruby rod and cutting a part of it and polishing it, and they were able to produce laser out of it. And this was done by Theodore H. Myman, who is a physicist at Hughes Research Laboratories. This is the first ever invented laser, and though it has a bit of disadvantages or complicancies in the output, this is the first, still recognized as the first ever best laser which is produced out. And further ahead, moving ahead, by the end of 1960, they were able to demonstrate the uranium laser, and this was done by P.P. Sorokin and Myrick J. Stevenson in Watson Research Center. So this didn't stop then, but by the mere end of the December of 1960, they could even enhance their knowledge of solid state onto gaseous lasers, where they were able to develop the helium neon laser by taking a glass tube and purging helium and neon in a ratio opposite to their atomic weights, atomic numbers, and then they were able to see the laser which is producing out, and this was able to overcome all the I can say negative drawbacks of the solid state laser which was invented by Myman. So this was done by Ali Jawan and his co-workers of Bell Labs. So this didn't stop by here, but till today, right from then advancing it to India laser and several other like carbon dioxide laser and different semiconductor lasers. Research is still going on till today, and it is now that we have to celebrate the laser, where it is celebrating its 60th anniversary. Why? Because we are in 2020. Okay, if you can understand, from 1960 to 2020, it is celebrating the 60th anniversary. And let's revise for your understanding the history of laser. It first started with the concept of Albert Einstein, where he could introduce the idea of particle wave duality of light, which we have discussed this part in the first chapter, which is quantum mechanics. And this concept they hold it on, and Charles Townes in 1958, where he started, have won the Nobel Prize in 1964, and this was even shared by not the Nobel Prize, but the work was even shared and even taken ahead by Arthur Shallow of Bell Laboratories. So both of them contributed a lot in framing the idea and discovering or inventing the techniques and the setup, the experimental setups and the needs for the mechanism to go ahead. And it is T.H. Myman who was able to recollect all these things and put it into work and put all the ideas and bring up the ruby laser. And this rapid development, it started from 1960 till today. And this is the first invention which happened in search of an application. Till then, the inventions were only in search of a concept, or to explain a concept, or to explain something which is hidden in the matter, like photoelectric effect, or the quantum mechanical concepts, or the electromagnetism principles, which were derived by Maxwell. If you take, they are just to bring something which is inside a material, or an answer to questions which are arising in the minds of the scientists then. But this laser, this is an invention in search of an application, because they want light to be advanced through stimulated emission, so that they know that it can be used for very good applications. Because when light itself of so much high velocity and it can be made to advance, it can be useful for many applications in materials especially. So if you move ahead, the lasers, if you see their applications all around you, you're using them in your laser printers and scanners, and you're even using in your normal PPTs as pointers. And if you see the main streams around you, you are using in defense and security for marking the targets they use and for guiding the ammunitions and the missiles when they are using the missiles to guide them, and even the electro-optical countermeasurements and the blinding troops also in defense and security. If they want to lead them, they are using these laser pointers. And the medicine and healthcare, if you see, we are now using very good ways of surgery where you are not using any knife, and this is a bloodless surgery, and you're even able to see what is happening inside you by just sending an optical fiber, and you just let the laser transmit inside, where it can even take the photographs of what is happening inside the human body. So the kidney stone treatment, even we are able to heal the kidney when it has stones by melting the stones, just because the pointer has very low divergence angle. It can just focus on that small stone area and it can melt it. And even dermatology, like this skin issues like the cancers and all, and ophthalmologist, the laser. And dentistry is, we are able to, without removing the tooth, we are able to see whatever is there inside the gum, and we are able to let it be healed by just posing that area towards laser. And even many other things, like if you, without disturbing the tissue of your skin, you can repair it if there is any infection inside it. And even the cosmetology, where you are using especially the Nd:YAG laser for advanced treatments of your skin. And in commercial and entertainment also, as I have told you, you are using 3D holograms, which is now even more advanced, and the laser light shows, which you know very well, and the decoration which you enjoy, and even the barcode scanners which you use in your library, and the laser printers, and which you take for your printouts, and the optical discs which are being operated in your laptops, and all these things, even the thermometers which you are now using to scan your body temperature without interacting with your body, which is now very much essential for you in the present situations of hailing in the climate. Okay, so lasers are much more advancing ahead, and these are very few of what I can tell you, and you can read the other things on the screen. So how are you seeing the laser being different from the light? If you see light, you are able to see that the light is diverged to a vast area, and it has a lot of wavelengths, and it is multidirectional, and it is very incoherent compared to laser, which is monochromatic, directional, and coherent. So what exactly is laser? Laser is nothing but light amplification by stimulated emission of radiation. So light, normal light, what you know and what the scientists still then know, they just amplified it by letting the radiation being emitted out after stimulation. So how did it happen? So they were able to, I will let you know how it happens in an effective way in my coming lectures. But this laser is brought out by using a device which produces a coherent beam of optical radiation when stimulated by electronic, ionic, or molecular transitions to the higher energy levels. And when they go to the higher energy levels, they return to the lower energy levels by stimulated emission, and thus the energy is emitted out. So if you see the features of the laser, which are of very high degree, they are coherence, directionality, and high brightness. And these bring a remarkable change for the lasers, or in the lasers, when compared to normal light, which is hence a reason for their large number of applications compared to light in many areas. So for this to understand, first you need to know the basic concepts of light when it is interacting with matter. What will it happen? Absorption may happen, spontaneous emission may happen, and stimulated emission may happen. In order to understand this, let's take two energy levels of a system, named E1 as the lower energy level and E2 as a higher energy level. The first option is the absorption. Absorption, in the sense, let us consider an electron of an atom which is there in the lower energy level. We know that suppose if there is some gap between E2 minus E1, let me say that it is equal to h nu. it's equal to h nu. Then if you can incident a photon which is equal to this h nu, only then this electron which is present there can absorb this h nu and it can raise to the higher energy level E2 minus E1. So once it raises to the higher energy level in which is 2, which is mentioned as 2 here, it has this h nu inside it. Okay, so this can be understood that the h nu photon which is there here, it is stimulating this electron which is there in the lowest energy level. That is, you can treat it as a vacant energy shells, which I have explained in my previous lectures of module 2. So the valence electron is getting stimulated or excited after being loosening from its shell, and it excites to the higher energies, which you have seen in semiconductors as the conduction band, right? For this to happen in semiconductors, we have seen that it has to cross the Fermi level. So here also, if it has to reach the higher energy, it doesn't simply happen for any photon what you give, but you need to give the energy which is sufficient enough for it to go. That means it should be equal to the difference of the energies between the higher energy level and the lower energy level. It should be minimum. If you give more than it, only you can go and reach the higher energy level. For example, if for you to understand more clearly, let me take E1 and E2, where E1 is the lower energy level and E2 is the higher energy level, and this is at rest in the lower energy level. So now if I give a photon which is of energy, the difference of E2 minus E1, let me take it as h nu, then what will happen is this photon will stimulate this electron and this will absorb this energy which is in the form of a photon and go and sit in the higher energy level which is E2, and now this has this photon inside it. So that is nothing but this is having the energy h nu inside it. So there is a probability for this electron in the higher energy level to stay only for certain time, which is its lifetime. Lifetime is nothing but what is lifetime of a charge carrier, of a carrier. So the minimum time or the shelf life up to which the electron can stay in any energy level is known as its lifetime, okay, energy level. So normally you say in spite of any, the lifetime you normally apply to an excited energy level, okay, or a higher energy level. Okay, so that is the lifetime. So the lifetime of the electron once it goes to a higher energy level is very low. So it cannot stay there for a longer time, but it itself spontaneously comes down. So it's a random process. It itself will come down. Okay, so because now, as you know, the electron which is there in the higher energy level already, okay, it's already there in the higher energy level, in the sense it is having an energy which is E2 minus E1, right? Only then it can go to a higher energy level, and it cannot stay there for a long time, but it spontaneously comes down. It spontaneously makes a downward transition, and as you know, when an electron jumps from a higher energy level to a lower energy level, it emits the photon. So it emits a photon out, which is equal to E2 minus E1, which is equal to h nu. So this is known as spontaneous emission. Now, if for suppose, let us consider that the electron is staying there for a time which is greater than its lifetime. That means it's not spontaneously coming down due to some reasons. If the electron is staying there for long time, and if you are letting it to be stimulated by a photon, then this stimulated photon, when it so the energy levels E1 and E2, the electron is there here, and you are letting it being stimulated by h nu. As I told you already, when the electron is staying there in the higher energy level itself, it has certain energy which is h nu inside it, right, which is equal to E2 minus E1. And now you are disturbing or stimulating it with an external photon. So what will happen? As we know already, when an electron is jumping from a higher energy level to a lower energy level, it will, from a higher, yes, it's not jumping, it's like making a downward transition from a higher energy level to a lower energy level. It comes down, and when it comes down, what will happen? It has to release the energy, whatever inside it. This it releases along with the photon which you have given, which is, so you get 2 photons out. Okay, so thus this type of emission of the electron which is staying in the higher energy level after being stimulated by an external photon is known as stimulated emission of radiation, which is the major concept or the principle for the laser to come out. Okay, so now you have understood this light is being amplified using this stimulated emission of radiation, and hence stimulated emission is the basic concept of this laser to be produced out. So these stimulated photons have unique properties. What are the unique properties? They will be in phase with the incident photon. If you take the incident photon and if you take the stimulated photons, they will be in phase with one another. I'll tell you more exactly. You can understand what is in phase and what is the same wavelength, what is same direction in the coming slides. And the stimulated photons will have same wavelength and they will travel in the same direction as that of the incident photon, and hence you will have worth enough properties in laser compared to that of light. So what are the differences for the spontaneous emission and stimulated emission if you compare them with respect to radiation? Spontaneous emission will be polychromatic, whereas stimulated emission will be monochromatic. Why? Because they both will be the stimulated photon and the emitted photon both will be in phase with one another, hence they will be of same wavelength. And coming to the intensity, this will have very low intensity, whereas this will be having very high intensity because of the next coming the directionality and the coherence. Coming to the directionality, it will be very highly directional. Why? Highly directional because the angle of divergence will be very large, that is increased angle of divergence. So you will get the beam which is very, when you on a torch, how will you find the beam? If you focus it on a wall, it will be very big, right? But when you take a laser, it will be very low directional, less directional, low in directionality, and because it has lower angle of divergence. You will understand this concept in the coming slides very nicely. And coming to coherence, if you take with respect to space and time, it will be spatially and temporally, like longitudinal wise and transverse wise. When you see the output of the beam which is coming out, the spontaneous emission will not be coherent, it will be incoherent, whereas the stimulated emission will be coherent spatially and temporally. And coming to the phenomenon, as I have told you, if you have an electron which is there in the higher energy level, it itself absolutely comes down, making an emission out spontaneously. Hence, it is known as a spontaneous emission. Whereas, if this electron stays here for a time which is greater than this compared to spontaneous emission, and if you are stimulating it with an external photon, then it leads to a downward transition, giving out 2 photons, which is h nu and h nu, because of the stimulated photon and the stimulating photon. So, this is the advancement of the stimulated emission in comparison with the spontaneous emission which you find in the normal conventional light sources. So moving ahead, if you see the properties of the laser, monochromaticity you can find out monochromaticity along with the other properties. What is mono? Mono means single. Chromatic means chromatic. You use this term when you are referring the wavelengths of that particular energy. So it has single wavelength. Laser, when it is coming out after stimulated emission, it will have single wavelength. Hence you call it as monochromatic. So what is happening here? When you take an atom which is transmitting between two energy levels in a material, either emission or absorption of the photon can take place. That's what you have understood till now. So this frequency, when this emission or absorption of the photon, its frequency will lie between that means the initial one, that is nu, or there will be an advancement which is nu plus d nu. So that means there is, what is nu? Nu is the frequency. So what is it happening? There is a broadening. So you call this as spectral broadening. And this spectral broadening may be due to three concepts. The first one is the Doppler broadening. This Doppler broadening is due to the velocity and the direction of motion when this emission is happening. So when this emission is happening, there will be a slight change of the frequency in the emitted radiation when you take the output because of the velocity of this change in the velocity and direction of the motion of this emitted particle. And if you see in the emission, there may even undergo the particle may even undergo collision. So when this collision is happening, a change in phase of the emitted radiation may happen, and this change in phase may lead to a shift in the frequency, and this will lead to the spectral broadening even. And this individual phenomenon which is leading to the spectral broadening is known as collision broadening. And normally natural broadening is nothing but when you take any particular wave, and when it is traveling in a medium, what will happen is there will be a change in its amplitude and phase when it interacts with the other medium or when it interacts with the other wave trains. So what will happen is this collision, when it is happening in this particular entity of atom, where you take an atom transiting between two energy levels, also a broadened spectral line may happen, which may be leading to the shortening of the wave train, which will lead to the natural broadening, which is one of the reasons for the spectral broadening event to happen. If you have to study this monochromaticity using this broadening, you can arrive at quantifying the degree of the monochromaticity, and this can be done by studying the wavelength spread. Wavelength spread is nothing but, if you have to understand this, first you need to understand what is wavelength. The wavelength of light differs for different lights. For suppose if you understand first what is wavelength. Wavelength is nothing but it can be distance between two maximas or the distance between two minimas. Okay, so for here for blue it is shown the distance between two minimas, and you can take like the distance between two maximas even as the wavelength. So here you can see that the wavelength of the red light is larger than the wavelength of the blue light, right? So if you're taking the wavelength as this and there is a spread of the wavelength, how can you take the spread of the wavelength? Before and after, you can just take this area and that area will give you the wavelength spread, and this wavelength spread can be written in terms of the spectral width. The spectral width is nothing but the spread of the frequency of the spectral lines, or you can even call the line width. In terms of the velocity of light, you can write it as this expression. And this wavelength spread, it will be different for different sources. Like for white light, if you see, it will be 300 nanometer. But if you see a gas discharge line, then it will be 0.01 nanometer. And for a laser, when you see, it will be 0.001 nanometer. You know, 1 nanometer is 10 raised to the power of -9 meters. That means if you take 1 meter, in that 10 raised to the power of 9, but that means after 1 you should keep 9 zeros, so that much part of it. So you can see how a conventional light source is being reduced down in terms of its wavelength spread. It is because of the directionality. Directionality, if you see in lasers, it is highly directional. Highly directional in the sense it is relatively narrow and it is only along a specific direction. If you see a light bulb as shown in the slide, it is emitted in different directions and the wavelength spread and the divergence is very much more. So directionality, when you see for the laser on the screen, you are seeing a very thin cone which is coming out, a narrow cone which is coming out, and when you see the relative beam width even will be different. Why is it? It is because this directionality can be understood in terms of the divergence. Divergence is nothing but how rapidly the beam is spreading after being emitted out. So if you have to understand it in terms of the spot size, you can understand it in terms of the spot size. So the beam divergence phi is given as 1.22 times the wavelength by 2 times the minimum spot size. So that will help you to arrive at the beam divergence. So for a typical laser beam, the divergence will be 1 milliradian. And if you want to understand how the divergence will the divergence be the same as the laser travels? No, it will not be the same. For suppose when I showed you in my previous slide, it was like this. So if I take from here to here the distance traveled as d1 and from here to here the distance traveled as d2, the spot sizes will be different compared from here to here. At d1 the spot size is like this, whereas at d2 distance the spot size has become a bit, yes, like this, right, like this. So there is a difference in the spot size. So this spot size, this spot sizes you have to take, and the distances you have to take the spot sizes as A2 at D2 distance and A1 at D1 distances, and if you substitute you can get the angle of divergence, and this angle of divergence will help you to understand how good the degree of directionality is. Okay, now the other thing is coherence. This is a very good property of the laser which is meant for the high amplified output which is coming out in comparison with light. So what is coherence? When you are studying the coherence of a wave, you have to take amplitude, that is the maximum displacement, and phase of that particular, if you are taking a wave at any one point you have to take. Then you have to correlate this point with any other point on that same wave. Then you can understand the coherence of that particular wave train. So if you take the light from a laser, it's said to be coherent. Means, what does it mean with coherent? It means that the wavelengths are in phase when you take it with respect to space and with respect to time. On the slide, when you see, you can see the incoherent light waves. For suppose if I draw a line here, a straight line here, you can see that for the first wave train and the second wave train, it is almost there is a shift to the right side for the minima, and when you see there is even more a shift in the third one, and when you see the fourth one, it is shifting to a maxima, and again there is a shift towards the minima. So it's not a shift, but it is itself the wave train. The wave train itself is like that. But when you are correlating one with the another, there is no coincidence. That means the crest of one thing is somewhere with the trough of the another. Okay, so you cannot say that these light waves are coherent. And when you see this diagram, when you take a line like this, you can see all the maximas falling on the line, and when you take a line like the second line on the minimas, you can see that all the minimas are fitting onto the line. Hence you call them as coherent light waves. The coherence can be taken in terms of temporal and spatial. Let's see what is temporal coherence. Temporal coherence means you can here see the amplitude and phase. When you take a wave train, you can correlate the amplitude and phase of this wave train at any 2 points P1 and P2 with respect to its displacement. How can you do this? You know this formula. Y, the displacement and phase can be written in terms of y is equal to a, the amplitude sine of 2 pi by lambda. Lambda is the wavelength into c, the velocity of light, t, which the instant, at any instant of time t you take, and x is the displacement. So here x is the instant of time at any point. It's not the displacement. At any point whatever you take. Okay, so it can be varying at whatever point you take. So if you are taking one particular point and if you are able to specify y, this should be the same for the another point on the same wave, then you call this wave as continuous. So that means if you are understanding it, P1, if you are able to see the amplitude and phase at P1, it should be the same at P2, or you should be able to recognize it at P2 even. Then only this wave train is said to be continuous wave. Otherwise, it's not continuous. For example, if I take something like this, if I take another one like this, and if I take like this, okay. So if I take somewhere P1 here and somewhere P2 here, the amplitude and phase will be different for P1 and P2. So they cannot be in coherence with one another. So this will happen. This is discontinuous wave. This is what you see in conventional light sources, because those are produced because of the spontaneous emission. So you cannot correlate the individual wave trains in conventional sources. Whereas in lasers, laser is produced because of the stimulated emission. And when you observe laser, the stimulating photons and the stimulated photons will be in same phase, and they will superimpose, resulting in an increase of the length of the wave train. For example, if I'm taking this is a stimulated photon, and you are again getting a stimulating photon. Okay, sorry. Yeah. Then if you see the resultant, you will see an increase in the amplitude and even the length. Okay, so there is an amplification in even the amplitude and the length also of the resulting wave train. This is the resulting wave train. So this is happening in laser because it has this property called as temporal coherence, and it is because these are continuous waves. You see them to be continuous. So if you want to see the maximum length of the resulting wave trains on which any 2 points can be correlated, that maximum length is known as the coherent length. Okay, if you are taking a coherent length, then if you take any 2 points, they can be correlated here in the resultant wave. If you take P1 and P2, P1 here and P2 here, these two can be correlated with one another. So that is such a wave train is said to be a resultant of the stimulated and stimulating photons, and that length of such a wave is known as a coherent length. And you can even determine the coherent time also. The coherent time is nothing but the time which tells us how long the particle can be in phase with the wave, or else I can also say that how long the wave passing through that particular point is continuous. Okay, so that is known as the coherent time. So the coherent time is given as the ratio of the coherent length and the velocity of light. The coherent length is always given as LC. So that is with respect to temporal coherence. If you see temporal coherence here, you are seeing it in terms of like this, you are seeing in this direction. So you also call this temporal coherence as longitudinal coherence. Whereas now, spatial coherence, in the sense you have to see the output of a beam, the laser beam which is coming out after stimulated emission of radiation, and if you see the cross-sectional area of it, If you see that both of them are in phase, okay, then you can call them as to be spatially coherent. For suppose, so this is the cross-sectional area of the output. If suppose I get some radiation out like this and something like, okay, like this, then what does this mean? It is, when you look at the cross section, there is no coherence. So the maximum separation between 2 points on the cross section, which are in phase, these two are in phase with one another, and this should be in phase all the time. Okay, then you call that they are spatially coherent. And here you are seeing in a transverse way, hence you also call this as a transverse coherence. Okay, so hope you have understood this. The final property of laser is brightness. So you see maximum brightness in laser compared to normal light. So even if you take 1 milliwatt of laser, it will be 1,000 times more than sun. Okay, such brightness it has. This is due to the coherence and directionality which we have seen earlier. That is the less divergence and spatially and temporally coherent. That is longitudinal and transverse wise lasers or the laser beam will be more coherent than the normal light. And if you are taking any two photons which of amplitude A, if they are in phase with one another, what will happen? The resultant amplitude will be A plus A is equal to 2A. And we know that intensity is always directly proportional to the amplitude. And now your amplitude is what? 2A. A plus A is equal to 2A. So now your intensity is 2A whole square, which is 4A square. So it is because of this amplitude. If you are taking for 2 photons, if it is 4A square, what is happening in laser? You are getting the stimulated emission of n number of electrons using n number of photons. So how much should be the intensity? It should be equal to Na square. And this is nothing but the coherent addition of the amplitude. And you see negligible divergence. And that's the reason why the intensity increases enormously and you see the brightness so good and so intensified that even 1 milliwatt is much greater than sunlight. And I would like to end this class by taking A.L. Swallows, one of the scientists who worked on laser even from the beginning. So where he said, this is my favorite quote which I want to share with you. Anything worth doing is worth doing twice. The first time quick and dirty, but please don't take this dirty for you. This is more applicable for research, especially experimental research. And the second time, the best way you can. This he has experienced through his research in lasers, and he has said it out. And there are many famous quotes of his. If you want, you can read and get motivated. Stay motivated and connect to me back in my next video lecture, where you will be seeing more properties of laser, where you will be seeing what are the conditions for the stimulated emission to come out continuously, and if you have to do so, what are the experimental arrangements and what are the conditions to do that experimental arrangements. And we may even look into the construction of the first ever invented laser, which is Maimon laser, which is the ruby laser. See you in my next video lecture. Bye. Wishing you the best. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.